In this video, we are going to do two things. We are going to color the final path so that it's easier for us to see the path when we're debugging, and we will also make sure that we can't cut corners when we generate the path. So right now, you'll see that there's also another problem when you put two nodes here and you press the generate path button. It actually also changes the color of the goal node here, and we wouldn't really like that because we would like to be able to find the goal node pretty easy when we do this. And another problem is also the fact that it doesn't create the arrows on the final path, and I would also like to be able to see the arrows on the final path. So let's do those two things first. If we go to the A-star debugger and we find the function called debug path, then we will have to make sure that it doesn't color the tile if it's part of the, or it doesn't color the tile if the tile is actually the goal, right? The same as we do down here in the close list. So we have to take this part of the close list if statement and copy paste it here. So we are sure that if the node is on the open list and it's not no goal or start, well, then we are going to color it. Then we're not going to color it, sorry. So if we play the game now, you will see that it should keep the original color. We run, as you can see, start is orange, goal is red, and you can see the open list here and the close list down here. But remember that the close list is not the final path, so we need to make sure that we generate the final path and color that one another color, because in some cases final path and close list is not the same. And besides that, we would also like to see the arrow so we can follow the path back and see if everything looks correct. We are creating some arrows right here. Point to parent under the for each loop of the open list, and we would also like to do that on the closed list, I think. So copy this one and paste it down here, and then if we save, let's see what happens. Click and click. And there we go. So now you'll see that we also have arrows on the closed list. So these were just two very small fixes here. Oh, let's try one more time. There we go. So you'll see that the path goes like this, right? So we also want to color the final path, and we can do that by adding. We can look in the A star here, and you'll see that we already created something called final path. And if we go to the final path, you'll see that the final path is a stack of nodes. So we'll have to tell our A-star debugger that it needs to take in a stack of nodes. So we can say stack node final, let's just call it path. So here we have our path, right? Then we have to make it for each loop. So we can say for each node in path. So each node in the path, if that node isn't our goal and our start, well, then we would like to color it. And then we can say copy paste this one, paste, and then we can say color.green. But there's a problem. A node that is on the closed list can also be part of the final path. So let's see, if we play the game now, you might not be able to see the actual debugging for the final path. And we also have to change the overload, because if we jump into the function called getPath, in the bottom you'll see we are calling the A-star debugger, and we're never giving it the final path. So we have to make comma final path, because we just defined that the A-star debugger function here needs to take in the path. So if you save this and jump to Unity, guess it didn't save. There we go. You'll see that we can't see the green color here, and that's because the blue tiles are on top of the green ones. So to fix this, we simply have to say, well, when we try to color something blue or create something blue, in here on the closed list, we will also have to say and then final path. The path was it contains node. So we will only make a blue tile if the final path doesn't contain it. In this case, all the nodes will not be in the final path or in the closed list, so all will be green now. So see, click and click, and there you go. So now you can see that we have these nodes that are green, which is the final path. And you'll also be able to see that we can actually let's get some more money first. Actually, let's go to game manager. Where are we setting the currency? Somewhere there. Let's say that we have $100 from the get-go, so we can just set some towers and test this out. So if we place some of these towers here, then you'll see that the final path and the closed list are two different things, right? Because all these around the start node are part of the closed list, but they're not part of the final path. The final path is what goes here. But as you can see, we are cutting corners, because right now if we have a character that walks here, it will actually walk over the tile from here to here and down here. We would like to walk with it so it goes up here, and then down. And maybe if you look at this here, you think that it might not be a problem, right? But if we do like this, start and goal, and if we do like so, then you'll see now it will pass through two towers, right? Because it shouldn't be possible for us to walk from here to up here, because this tower up here is in the way. And to fix this, we need to make sure that we can't walk up here if there's a tower above us and next to us. So we need to make some kind of check so we don't do this move here. Instead, it would have to go all the way up here, around, down here, around, down here, and then like this. So let's say we are playing the game and we need to move down here, right? We want the character to move down here. If I want to make a move to this node here, I need to make sure that there is no tower right here and no tower right here. So in these two positions where there are towers, I'll need to make a check to make sure that there are no towers here before I actually make sure that it's okay for me to go down here. So let's make a function that actually does this check for us. So we'll never go down here if there's a tower here or here, because that will make the monsters go through and on top of the towers. So to fix that, we need to open up our A* script, and if we look for it here inside the if statement, where we set the else statement, where we set the cost to 14, we will have to call a function, because we know right here when we set the cost to 14, we know that it's a diagonal move. So we need to make that little check we just talked about before, right? Where we check if I want to go down here, that this one is free and that this one down here is free. And if I want to go down here, I need to check that this one is free and this one is free, and so on. So here we need to make a check, and we can create a new function down here. It's a private function called connected diagonally. And it takes in the node, which is our current node, and it takes in the neighbor. Okay, if I can spell correctly. And it returns a bool. Okay. So is our A* static? It is static, so we need to make this private static as well. So now we need to return something. So this function here can return true or false. So we basically asking the function, am I allowed to go down here? So am I connected to this node? If I'm connected, then I'm allowed to go down there and I can take it as part of a path. And if it's not connected, then it's because there's a tower in one of those two positions we looked at. So up here, we can say if our, let's say, if connected diagonally, and we need to get the node, the current node, and we need to get the nodes neighbor position. So this is the neighbor node. So we have the two nodes. We have our current node and the neighbor node. So we can figure out how to go from one to another. And if that's the case, if they're not connected diagonally, which means that there's a tower in one of those two bad positions, then we simply say continue. And what continue does is that it jumps to the next loop. So it doesn't do all the calculations down here because it's not going to be part of the path. So it executes the continue. So it jumps up here and goes to the next loop in the loop. Next execution of the loop, so to say. So that makes us skip that. So first of all, we need to figure out which direction we need to move, because when we know the direction, then we know which nodes we actually need to check to see if there's a tower on them. So we can make a point and call it direction, and it's equal to neighbor dot position grid position minus current node dot grid position. So it is complaining that we can't take a grid position and minus it another grid position because it's type point. Well, we can go to our point here, our point class, and inside the point class we'll have to make sure that we can use that operator on it, because we're already able to check if they're different or equal. So we can make a public static point operator minus, and we take point x and point y. It's operator with non-capital, I think. There we go. That's why it's complaining. And then it needs to return new point, where we say x dot x minus y dot x and x dot y minus y dot y. There we go. Okay, so now we just wrote the code for taking one node and subtracting it from another node's position, right? 1 point, sorry. So we wrote the code for subtracting a point from another point. So when I say, let's see, where was it? It was inside our A star, sorry, here. So when I say neighbor dot grid position minus current node dot grid position, well, it actually executes this function here because it's on the point. So it takes the x value of both nodes, reduces them, or subtracts them, I think it's called, and then it takes the y values of both nodes and subtracts them. So, and then it returns the point. So we get the actual value called direction, because it's this one minus this one. So now it's legal for us to do like that. Remember that there are two nodes we need to check. There is an upper and a lower. We do like this. We have a upper node here we need to check, and a lower node down here, we need to check to be able to walk through this path. And in this case it's not legal because there are towers in both positions. Also, if there was only one tower, it was still not legal for us to do that move. So we can make a point, and this is the first check. It's a new point, and it's equal to current node dot grid position dot x plus our direction. And comma current node dot grid position dot y plus direction dot y. And I also need to write direction dot x here. There we go. Okay. So what just happened? Let's say that our direction here, it might be equal to minus 1 point minus 1, right? Then we take our x position, our current position, and add the minus 1 to it to figure out what the x position of the first tower we need to check is. And then we take the grid position y of the current node plus minus 1, because that's the other direction. We go minus is this way and then down here, for example. So that means that we need to check this direction down here diagonally. Maybe it's easier if I do like this. If we do like this wide, doesn't make sense that way, sorry. If it's -1 and -1, right, then we know it's this direction and down here. So it's this way here we need to check, which means we need to check this node here and this node down over here. And to do that, we can calculate the first position, which is equal to the current x position plus the x direction, which is this node down here. So let's say that there was a tower here we need to check. So we're checking this node down here because the y keeps being equal to the y. So because I just said that, I know that I don't need to check the y here or change the y. So we take the x position plus the direction, which in our case was -1 here, and we take the y position, which is also the same, so it's this one we're checking. So that's the first check. Sorry if I'm stumbling on my own words here, but I need to figure out myself what I was saying. So second is equal to new point, and we take the current node.grid position .x, comma, current node.grid position .y plus direction.y. So now we need to check that one below it, right? To check the one below it, we say current node.grid position .x is the same, so we stay on this x position. And what else? Then we need to say current node.y position -y, which is -1, so we don't go down here and check this node. So this is the node here we're checking. And if that one has a tower on it, well, then we can't move in the direction we want to. So now we have the first, which is this one we need to check, and the second, which is this one we need to check. So in that way, by doing these two lines of code, we'll get the positions of the nodes we need to check for towers. I hope it wasn't too confusing. So, okay, so we can make two if statements to check this. So if our level manager, that instance that in bounds, first of all, we need to check if that position is in bounds. So we check if the first position is inside the map, because there's no reason to do any of this if it's not inside the map, right? And if the level manager, that instance, that tiles first dot walkable. So we will make sure, I actually think walkable should be like this, walkable. Anyway, we need to make sure that our node is walkable, because if it's not walkable, then there's a tower there. So if the node is inside the grid, it exists, and our level manager instance, if our tile isn't walkable, well, then we know we are not allowed to go down there, so we return false. Then we make an if statement here. If our level manager that instance that in bounds second, so if our second is in bounds and our level manager that instance the tiles second dot walkable, so if our second is also not walkable, then we return false. Okay, else we return true. So if none of these two evaluates to true, if for example, if let's say that our level manager, that instance, if the first one is walkable and the second one is also walkable, well, then we can return true, because then it's totally fine to walk down there. So we can go up here, and then you'll see we have the if statement here that checks if we are not connected diagonally, we continue, else we calculate the g-score and move on to calculate everything for our nodes and add them to the correct lists and move them on to the final path in the end, and so on. So now we have a way of checking if our nodes are connected diagonally based on the towers around the nodes. So let's try this and this, and if we add some towers here, you will see that they're walking perfectly around it, right? Here I'm able to walk diagonally, and then it goes up here, all the way around, down, down, down here, instead of going up here and going directly to this one. And you'll also see that if I do like this, like so, you'll see instead of jumping up between the two towers here, it actually goes back around this one, so it gets a perfect path instead of walking through the towers if the sprites are too big and so on. At least that's how I would like it in my game, so that they don't cross over two towers like so. So that is what we needed to do in this video, so thank you very much for watching. In the next video I think we'll start spawning some monsters in the game, because now we have our final path, so we can actually create our monsters and then we can feed the monsters this path so they can walk from start to goal. And yeah, thank you very much for watching, and remember to follow me on Twitter, like my Facebook page, and subscribe to the channel if you haven't done it already. Also remember that InScope Studios is a community founded page, so all your support is very, very important to me. You can support me in different ways. You can go to the top link and go to the Patreon page and get some different perks, like all the projects that I've ever created for this YouTube channel, or you can go to the bottom link and get one of my projects as a standalone product if you want to. So thank you very much for watching.